Dear students, in this video we are going to study about eddy currents, the demonstration and drawbacks of eddy currents, applications of eddy currents in induction stove, and eddy currents in brake system in the trains, eddy current testing, which is also called as non-destructive testing, and electromagnetic damping in galvanometers. Now let us study about eddy current. According to Faraday's law of electromagnetic induction, an EMF is induced in a conductor when the magnetic flux passing through it changes. However, the conductor need not be in the form of a wire or a coil. It may also be like a metal plate like this. So, even for a conductor in the form of a sheet or plate, an EMF is induced when the magnetic flux linked with it changes. But what is the difference? It is that there is no definite loop or path for induced current to flow away. So, as a result, the induced currents flow in concentric circular paths as shown in this figure 4.110 like this. So the eddy currents will be in this circular form, in this metal plate. When we apply an alternating magnetic field, is created like this because of the alternating current which is passing through this coil. So these electric currents resemble eddies of water, and therefore they are called as eddy currents. They are also called as Foucault currents. Now we will see how these eddy currents are produced by this demonstration. Now here there is a simple demonstration for the production of eddy currents. For that, let us consider a pendulum that can be made to oscillate between the poles of a powerful electromagnet as shown in this figure 4.11a. So this is a pendulum which is made to oscillate between the pole pieces of this magnet. This is north pole and south pole, and this pendulum is oscillating between the poles. First, the electromagnet is switched off and the pendulum is slightly displaced and released. It begins to oscillate and it executes a large number of oscillations before stopping. The air friction is the only damping force in that case. And here the coil is wound on this magnet through which current can be allowed to flow if we switch on this. So before we switch on this electric circuit, the pendulum will oscillate many times before coming to rest. But if you switch on this circuit so that the current is passing through this coil, then these oscillations will be reduced. That is, the number of oscillations will be reduced because of the eddy currents produced in it, and that will actually oppose the oscillation of this pendulum because of a heavy damping force of eddy currents, which will bring the pendulum to rest within a few oscillations itself. So that is shown here in this diagram 4.11b. But if you have some slots in this pendulum, that means some slots are cut in the disc as shown in this figure like this. Some slots are cut in this pendulum. The eddy currents will be reduced, and therefore the pendulum will now execute several oscillations before coming to rest. So this clearly demonstrates the production of eddy current in the disc of the pendulum. Now, what are the drawbacks of eddy currents? When the eddy currents flow in the direction, a large amount of energy is dissipated in the form of heat. So the energy lost due to the flow of eddy current is inevitable, but it can be reduced to a greater extent with some suitable measures. Where these eddy currents are being applied. So if you want to design a very good transformer core and electric motor armature these eddy currents play a crucial role. So we have to minimize the eddy current loss. In the case of a transformer core and the electric motor armature. To reduce these losses, the core of the transformer is made up of thin laminas insulated from one another, as shown in figure 1.2a, like this. So these are of the laminated core. You would have seen this kind of transformers. And while for electric motor, the winding is made up of a group of wires insulated from one another, like this. So this is an insulated winding of an electric motor. The insulation used does not allow huge eddy currents to flow, and hence losses are very much minimized, reduced, like this. So where this eddy current is applied, in this case of a spherical stone and a spherical metallic ball of same size and mass, when they are dropped from the same height, let us see which one will reach the Earth's surface first. And if we are assuming that there is no air friction, you will just think that the stone and the spherical metallic ball will reach the ground at the same time, but actually the stone only will reach the Earth's surface earlier than the metal ball. What's the reason? That is, when the metal ball passes through the magnetic field of the Earth, the eddy currents are produced in it, which will actually oppose its motion. As no eddy currents are produced in a case of stone, it will fall free. Therefore, it reaches the ground first. Next, so here there is another pendulum with a strong magnet suspended at the lower end of the suspension wire. So you have to make it oscillate with the glass plate below it and note the time it takes to come to rest. So you are next placing a metallic plate below the oscillating magnet, as shown here. First we are pressing the glass, and here the metal is placed, so that there is a rapid damping of these magnetic oscillations. So in this second case, the magnet stops soon because eddy currents are produced in a plate which opposes the oscillation of the magnet. Where these eddy currents are being applied, let us see that. Though the production of eddy current is undesirable in some cases, it is useful in some other cases. A few of them are given here. The first one is about the induction stuff. Next, eddy current brake, eddy current testing, and electromagnetic damping. Let us see one by one. The first case of induction stove, you would have been using that for cooking food, and that will be done very quickly and safely with less energy consumption. And below that cooking zone, there will be a tightly wound coil of insulated wire, and the cooking pan made of suitable material is placed over the cooking zone. As shown here, this is the induction stove, and this is cooking zone, and coil, and cooking pan. So when the stove is switched on, an alternating current flowing in the coil produces high frequency alternating magnetic field, which induces very strong eddy currents in the cooking pan. So the eddy currents in the pan produce so much of heat due to dew heating, which is used to cook the food very quickly. So that is shown in this figure. What will be the high frequency produced? Usually we get frequency, there is a AC frequency of about 50 to 60 Hertz for our domestic purposes, and that frequency will be increased to 20 to 40 kilohertz before giving it to the coil in order to produce high frequency alternating magnetic field. Next we will study about the eddy current brake. This eddy current braking system is generally used in high-speed trains and roller coasters. Here strong electromagnets are fixed just above the rails, and to stop the train, electromagnets are switched on. The magnetic field of these magnets induces eddy currents in the rails, which oppose or resist the movement of the train. So this is eddy current linear brake as shown here in this figure 4.14a. Linear eddy current brake like this. There is a linear eddy current brake, which is clearly shown in this diagram. But in some cases, the circular disc connected to the wheel of the train through a common shaft is made to rotate in between the poles of an electromagnet like this. When there is a relative motion between the disc and the magnet, the eddy currents are induced in the disc which stop the train. This eddy current circular brake. So this one is called the eddy current circular brake as shown in 4.14b. So this is a linear eddy current brake and this one is circular eddy current brake. Next we are going to study about the eddy current testing. It is one of the simple non-destructive testing methods to find defects like surface cracks, air bubbles present in a specimen. A coil of insulated wire is given an alternating electric current so that it produces an alternating magnetic field. And when this coil is brought near the test surface, eddy current is induced in the test surface. The presence of defects causes a change in phase and amplitude of the eddy current that can be detected by some other means. So in this way, the defects present in the specimen are identified, like as this is the diagram, which is having a conductive material. Eddy currents are produced in this material by applying an alternating current to this coil, which will produce a magnetic field around it. Next, we are going to study about electromagnetic damping. Here, in this case, the armature of the galvanometer coil is wound on a soft iron cylinder like this. And once the armature is deflected, the relative motion between the soft iron cylinder and the radial magnetic field induces eddy current in the cylinder. The damping force due to the flow of eddy current that will bring the armature to rest immediately, and then galvanometer shows a steady deflection. So that is called as electromagnetic damp.